All right. Good afternoon, folks. My name is Sree Kuchibhotla, and I'm a developer in the GRPC team. So today I'm going to talk about the C-Core architecture and also the life of an RPC. So I must warn you that I have a lot of slides. I'll try to go through them as quickly as possible and try to leave some time in the end for Q&A. All right. So who is the target audience for this talk? This talk is primarily aimed at like power users of gRPC, someone who uses gRPC in their application, who may have had to debug any issues, who may have had to look at some of the gRPC traces in the process. Hopefully, this talk will help you understand at least the big picture, right? Anyone either contributing or thinking of contributing, they might find the talk useful. Or anyone just curious about gRPC architecture, just understand what's going on. So, all right. So gRPC is implemented, gRPC has idiomatic APIs in over 9 languages. Actually, I excluded a few, but over 9 languages, and it has it is natively implemented in 3 languages, Java, Go, and C. All the other languages are wrapped around the C implementation. So my talk is primarily going to focus on the C-Core architecture. I'm just going to refer it to as C-Core from this point forward. Before diving into the details, it helps to sort of set some context on. Most of you may already know this, but what are some of the key features? And this is primarily, these are some of these are core specific. So it's payload agnostic. gRPC core does not know anything about the payload, doesn't know about the serialization format, whether it's protobuf, flatbuf, it doesn't know. That features are implemented in the wrap language layer. And then it has extensible architecture. The actual functionality of core stack is very lean. Most of the value add functionalities come from what we call filters. We'll see later in the presentation. So filters provide a lot of value add functionalities like authentication, tracing, service discovery, a bunch of other stuff. Even deadlines is implemented as a filter. gRPC works with many transports. By default, it uses HTTP2. It's built on HTTP2, but it can use other transports. We have implementations running in production using other transports, like Cronet or Quick, which is UDP-based, and a few more. It is the API of core, and most of the architecture is designed by keeping performance in mind. There's a lot of optimizations we do, a lot of design choices. That's probably a different talk, so I won't be really getting into that aspect in this talk. Okay, so now let's sort of look at the architecture of core. So core is divided into 3 layers. The topmost layer is aptly named the surface layer, which itself is divided into 2 parts. One part is the API layer, which provides the C-Core API, and below API layer sits the filter stack. Those are the ones that provide all the extensions I talked about. Again, just to remind you, we do not encourage applications to directly call or talk the C-Core API. They typically use the wrapped language APIs, and the consumers of this are the wrapped language APIs. So I just wanted to make it clear. The second is the transport. Transport implements the wire protocol, right? And by default, it's HTTP2, but you can use other transports as well. And at the bottom layer, you have the I/O manager that provides low-level networking I/O functions, network utilities, timers, and a bunch of primitives that are sort of platform-specific. Most of the components here tend to be platform-specific. We support multiple platforms. There's Windows-based implementation. There is POSIX-based, and multiple versions depending on the specific kernel you're using. Not all kernels have all features. So there's a lot of platform-specific code at this layer. Okay. So again, before diving into the life of an RPC, I just wanted to take a couple of slides to talk about some of the common terminology, or the class of objects that we very commonly use in core, right? I mean, and also it helps to understand the relation between these. So let's start with a channel. A channel is a communication pipe between a client and a target, and I'm deliberately not using the term connection to describe a channel, and we'll get into it later. So channel is a communication pipe between a client and a target. A call is bound to a channel. The relation between a call and a channel is many to one, so that means you can have multiple calls on the same channel. And then you have a bunch of operations that could be performed on a call. I'll talk about it in the next slide. So really core, when you're talking at the core API, all you're really doing is these operations on a call. The so-called unary RPC and the streaming RPC abstractions that the higher wrap languages provide are really composed of these low-level operations. We'll look at that a little. And these operations are done in batches. So batch is an important concept. A batch can contain operations. A batch can contain one or more operations. And then finally, the most important concept here is this notion of a completion queue. So when you start a batch of operations, you wait. The completion of the batch is notified on what we call a completion queue. So typically, clients and servers interacting with core, the semantics are something like they start a batch of operations and then they wait. They poll the completion queue to see if the batch completed. And the core is the one that posts the completion to the completion queue. So that's typically the semantics. Like all the APIs are essentially, if you look at it, they follow that pattern. Just sort of trying to bring it together. So those are the ops that we support. I'm not going to read them out loud, but the interesting thing there is, just wanted to highlight that, the messages that are exchanged between client and server are pretty similar. So client always starts by sending the initial metadata, followed by 0 or more messages, followed by trailing metadata, and server does the same. In case of unary RPCs, there's exactly one message that's sent from the client, which is essentially the parameters. Initial metadata from client to server in all RPCs essentially contains stuff like the method name, encoding type, or any other custom metadata. We expose APIs for applications to send their own custom metadata. Trailing metadata from client to server is just end of stream indicator. Server to client initial metadata again has the same encoding type. If it's a unary RPC, the message contains the return value from the server. Trailing metadata contains the status, whether the RPC, the error code, if the RPC failed. All right. So I think we are ready to dive deep into life of an RPC. So it starts with a channel creation. And I'm dividing this into two phases. So first part, I'll focus on the channel creation workflow. And the second part, I'll focus on call creation and the life of a call over this channel. So that's the client. As I mentioned before, completion queue is a very important construct. So the client starts by creating a completion queue, and then a thread waits on the completion queue for events as much as it can. Right? We always that's a contract we expect from the users of the consumers of GRPC core. So client creates the completion queue. Client then calls an API to create a channel and passes the server's URI, and that creates sort of a filter stack specific to that channel that is in creation. So there are a bunch of filters, but the interesting filter there is the client channel filter. That's the one that sort of orchestrates the service discovery and load balancing part. So the client channel then calls the resolver. Resolver is pluggable. There are multiple resolvers that we support. And then the resolver returns you a list of addresses that the URI resolves to. So URI, a single server URI might actually resolve to multiple backends. So I might be referring to the term backends and addresses interchangeably, but essentially, when I say backend, it's one of the addresses that the resolver resolved. So the resolver returned a bunch of addresses, and I listed the resolvers that that the GRPC open source version has. All right, and then the client channel filter then creates an LB policy that's associated with that channel, and keep in mind that this is a client channel load balancing. I think we had a talk yesterday by Jan that talked about load balancing, and so this is the client channel load balancing. So then the client channel filter then initiates connections to all the addresses, all the backends returned by the resolver. So yeah, here basically we see connect requests being sent to every backend. At this point, I should mention that this process is typically done in a lazy fashion. Like when you create a channel, it doesn't always immediately do that. We wait until the very first call is created on the channel. But for illustration purposes, I'm just showing it here. So anyway, so the client issues connect to all the backends. And just let's look at one of the backends. What happens on one of the backends? So the server IO manager receives the connection, accepts the connection, so that acts back to the client. It also notifies the surface that, hey, there is an incoming channel. So server creates a channel object, thereby initializes the filter stack on the server. It's pretty similar to the client side, except a few filters that are client specific, like client channel. And at this point, the server is done. Server has done its part of channel creation. Now, the client gets, server has sent the accept message, so client gets the ACK. Client's IO manager tells the channel filter that, yeah, one of your backends accepted. The client channel filter then creates what we call a subchannel. So this is something that I didn't introduce before. So creates what we call a subchannel to the particular backend. And each subchannel comes with its own set of stack of filters. And that's it. Once it creates a subchannel, now you have a subchannel that is established. In the meantime, the other backends also might have responded. So that results in subchannels being created for the other backends. And in the end, you end up with what I just showed here. So you have a bunch of subchannels, each connecting to one of the backends. And so the one thing I wanted to highlight is, so really all these subchannels are part of a channel. So channel is really a collection of subchannels. And the subchannel is the one that maps to a connection. All right. Now let's move on to life of a call. Just to keep things simple, I'll talk about unary calls here, but streaming calls should be very similar. It's really, the difference is just based on the number of messages being transmitted back and forth between client and server. So let's pick up from where we left off. So we were at this stage, where client created a channel. It ended up with a bunch of subchannels, and I'm showing one such subchannel, one such backend. Now, client applications call an API to create a call. So that creates some memory for a call object. Keep in mind that at this point, this call is not bound to any of the subchannels. Right? We know that the call is bound to a channel. We are creating a call over the channel, but it's not bound to a subchannel. So that happens only when some operations are started on the call. Right? So client starts a batch of operations. So it's a unary call, so it has to start a batch of operations. I'll talk about the batch of operations in the next slide, but I just wanted to show what happens when a batch is started. So since it's the first batch, depending on the LB policy attached to the channel, one of the channels is picked. So when I previously mentioned about LB policy, I forgot to mention what kind of client-side LB policies we support. So we support 3. GRPC supports 3 LB policies. So one is pick first, That's the default, so it just picks the first subchannel. Other one is round robin, so it just keeps round robining over the subchannels. And the third one is what's called GRPC LB, which is the look-aside load balancing. So I have a link in the slide that talks about load balancing. So anyway, so let's assume this is the subchannel that was picked. Whatever might be the LB policy, but this is the subchannel that was picked. Now from this point forward, let's sort of simplify our diagrams. So I'm only including the components that are important. So we have a call, there's a subchannel, client and server, and completion queues on either side. So yeah, where we left off was client started a batch of operations. And so since it's a unary call, client just starts a batch with all the possible ops, right? Why did it start a batch with all the ops? Why not split send and receive into two different batches? It could, but there's really no need, as we'll see. Because it's a unary call, it can just send all the operations in one batch. So the client starts, like once the client starts the batch, initial metadata is sent, followed by the message, followed by the trailing metadata. And now, so three of the steps in the operations in the batch are done, but the batch is not complete yet because there are 3 more. So client is just waiting for those to, when I say waiting, it's polling the completion queue. It knows that once the batch is completed, the result will be posted on the completion queue. So it's just wait, the client is, the expectation is that the client will be polling the completion queue for the result. So now at the server sees the initial metadata, so more specific, to be more specific, it's the IO manager side of the server that sees the initial metadata, reads off a few bytes, passes it to transport parses it, realizes it's initial metadata, and then notifies the surface that, yeah, you have an incoming call. So then surface on the server realizes that, okay, there is an incoming call, so what do I need? And it notes, based on the method name, it knows that it's a unary call. And then it says, okay, let me start a batch. I know that the client is sending message and trailing metadata, so let me start a batch to receive initial metadata, receive message, and receive trailing metadata, right? So it starts a batch. And that, since all the messages are already on the byte, this batch completes typically very quickly. So once the batch completes, a notification is sent on the completion queue. The thread picks it up, now calls your higher layer application handler. So this is your RPC implementation. Like this is your unary RPC implementation. That is called. So that one thing I didn't show here is client calls the wrapped language, which deserialized it, and then called your handler. So, and then your handler, the application handler, performs the operation, writes the result back. That essentially results in another batch of operations, right? So it is sending its initial metadata. It is sending a message that contains the response of the unary call and trailing metadata that contains any error code. And once that batch is complete, the server is pretty much done with the call. The call is complete on the server. On the client, so recall that client is waiting for a few ops, right? So client now reads the initial metadata, reads the message, realizes that the batch is complete, posts a notification on the completion queue, and batch is done on the client side. Application thread picks up, call is complete on the client. So this is unary. Streaming is pretty similar. Like it's just that the number of operations in the batch are different. Like because a client initially, the only difference is that client cannot, in a unary call, all the operations were sent in one batch, whereas in a streaming call, typically client sends initial metadata and then sends each message as a separate batch because it doesn't know like how many messages might be sent. That is a variable number. So that's, other than that, the flow is pretty similar between client and server. So that's good. I did better on time than I thought. So we have 15 minutes per questions. So hopefully all of you found at least something useful from it, some takeaway. I certainly did when preparing this. I mostly work on the I/O manager and transport components, and I know enough to debug issues at the rest of the stack, but not in this much detail. So I certainly learned, and so I definitely encourage you to please contribute. And these are some of the additional resources. So cool. So we have about 15 minutes for Q&A. So that's great. Yeah. Yeah, thanks.
Hi, thanks. So from what I understood, when setting up the channel connection, the actual network connection to the server is not set up at that point. So when I start a channel, I have no knowledge if the servers are reachable, or is there some kind of acknowledging traffic?
Correct. By default, that is the behavior. You wouldn't know whether the server is reachable. So you wouldn't know until the first call is sent. But there is a way. I mean, there are APIs. If you really want to know, if you want to be certain that that the servers are reachable, there is an API to force the connection before any call is sent.
So I can check connection is up and running.
Yes.
Okay. And second question: when the server sends back the response to the client, is there any acknowledgement to the server that the client received the traffic?
When the server sends the response back. Could you repeat the question?
The server sends the messages back to the client. The client receives. Does the server get any notification, like TCP acknowledgement, that the client actually received all the data, or is it just
not at the GRPC level? Sure, you'll have TCP level X, but not at the GRPC level.
Okay, thank you.
Yep. I can repeat the question. Yeah.
So like the new GRPC version comes out like 1.9.
Uh-huh.
My apps to 1.8. Like what are the guarantees, or then I don't know. Then I have to. So my server is at 1.9, then I go back to 1.8, and like what are the guarantees for the version numbers?
Yeah, I mean we try to maintain wire compatibility between versions, but
fully backward compatible. Yeah. We follow semantic versioning, so 1.0 will always map.
In the streaming scenario, since you have a completion port and a lot of messages, do you guarantee the sequence of the messages?
Yes, we do. Messages on a stream are guaranteed to be retrieved.
So you have
in the order, in the order they were put on the channel.
So you have a serial number for each message.
Yes. This one.
Hi, thanks for the presentation. How do you deal with application error, timeouts, or anything like that?
There are many ways. So you can set a deadline on an RPC. When you create an RPC, you can set a deadline. So if for whatever reason your RPC handler got stuck or taking forever, every RPC has a deadline, so RPC gets cancelled. Similarly, you can also force cancel an RPC, both on client and server. Does that answer your question, or were you? Yeah, okay.
Thanks. When you enable tracing in gRPC, does it add a filter in that core block, or it's handled by the language wrapper? Like on the gRPC call, you can enable tracing and add some options.
Oh, in the gRPC core?
Yeah.
Those are just actually printf statements. They're logging out to your std out. The traces that you're talking about are not coming from a filter.
Okay.
Yeah.
Thank you. when you're running in a multi-threaded environment, how much of these channels and sub-channels are shared?
When you're running in a what environment?
Multi-threaded environment with multiple threads in your client, for instance.
Oh,
so
I
running
see.
in parallel, how much of this is shared?
So, like, there is multiple calls can go on a channel, right? And there is no, and channels are completely thread safe. So you can, like, there's actually no correlation. Multiple threads can call APIs to start a call on a channel. Does that answer your question, or what did you? Oh yeah, lower part. So we do have some optimizations in the stack. So let's say you created 2 channels to the same target, right? So let's say the server URI resolves to only two backends, but you created like 10 channels because you wanted to parallelize in your application. So you created 10 channels to the same URI. They'll still use the same underlying sub-channels, right? So we do that. So there is no explosion of connections there. We try to reuse the connections, the underlying connection as much as we can, which is something I didn't talk about. But so if you have 2 channels, they still essentially use the same sub-channel. So there are some optimizations there.
Do you keep a full backlog of the messages and the batch processing when a connection fails, so you automatically roll over to another sub-channel, or do you just trap it out?
If a sub-channel is disconnected for whatever reason, the call is cancelled. There is recently retry support that was added, so it will retry depending on the error you got back. If it's a retryable error, we retry, but the call is effectively cancelled, and it's up to the application to initiate a new one. Yeah.
So there's also this gRPC feature that you can annotate your HTTP 1 API with options in the service.
Okay.
And there's also Google Cloud endpoints where you can do this way, or with a YAML extra file. Is there like is this tool open source as well, where you can do the YAML specification? Because I only found the inline option thing.
I'm actually not familiar with that.
I think the tools are open sourced in Google Cloud APIs, Google APIs repository. They've been used mostly for internal purposes, but they are open sourced and usable, just not very friendly at times. So you should be able to use, but at your own risk at this point of time. And yeah, Cloud Endpoints tries to make them easier to use as a product.
Yeah. Looking for the YAML thing, which does, you can describe authentication.
Right.
You can't do it in the gRPC, in the protocol you can.
Right, yeah.
Is there a limit of the number of threads open in the server side in the concurrent?
Is there a limit on the number of server threads? There isn't. There isn't at this point.
Are there any specific features or improvements you'd like to see in the coming year or so?
That's a good question. So, I mean, from the core perspective, the things that we are currently working on very actively is to make the performance even better. The performance is actually quite good, but there's still a lot of room to improve. So that's been one of the focus. The other focus is also on sort of some of the code cleanup, like making the filters. It's not exactly super easy to add a new filter if you want today. So like, we are working on that to make it easier. Are there things you want to add, Jayant?
I'll add. So there are 2 big features, and we would love help on those also. One is retries, and retries is fairly complex because it's doing transparent retries as well as policy-based retries and hedging of requests, so you can hedge requests at multiple. So that's one big feature, and second is called service config. So what service config does is basically allows a server to specify a config and client honors it. So when you deploy and you want to say change time, you want to instruct the clients to change deadlines because you updated server, then you can do that on the running clients and servers through service config. So those are 2 big features that we are kind of have proposed and are working on, but would love to get those out.
How do you ensure feature parity between the C-Core and Java Core or Go Core?
Sure, a good question. So how do we ensure feature parity between C-Core, Java Core, and Go Core? So first, the wire protocol is pretty clear, and we run a bunch of interop tests, like very regularly, with various. It's a matrix of clients and servers, and that catches most of the issues.
So we don't add any feature without interop spec and test.
So do you test sort of end-to-end each, or do you have isolation of testing cores against each core? Or sort of
It's end-to-end.
End-to-end.
Yeah. This one over there.
How much of GRPC's design was influenced by like Stubby and other internal Google RPC mechanisms?
I can answer a bit, and maybe Jayant can add more. The completion queue model and the threading model is completely different from Stubby. So that being very different, and the code really, they do not share any code at all. So it's completely written from scratch. However, many of the components are inspired by Stubby design, like the polling engine. Like Stubby's polling engine has been battle tested, highly optimized. So many of the ideas at that level, at that granularity, are heavily inspired from Stubby. You want to add anything? Yeah.
No, I think it's mostly the ideas came from Stubby. We've shared whenever we can, but we updated the protocol, so it's HTTP2 based, so anything HTTP2 specific is new. And our async models switched to being a completion queue based. This is only for C-Core instead of being a callback based, which is what we used in Stubby.
Are there any significant performance differences between the implementations in Java, Go, and C? And how is ensured that those are really equivalent and behave exactly the same? So,
significant performance differences. There are performance differences. The C++ version is generally faster than Java and Go implementations. And what was the second part of your question? Like, how do we?
How do you guarantee that they are equivalent behavior?
How do we guarantee equivalent behavior? The same interop. We do interop testing. Very almost continuously. So
yeah, and all interop tests, and we have all the performance dashboards also in open, so you can see across languages performance.
Yep, that's right.
So instead of looking forward, like looking back, are there any things that if you could go back and do again that you would change or maybe do it slightly different way?
That's a good question. There's a lot. Maybe I'll rewrite everything. I'm just kidding. But probably the layering, we would have probably implemented it a bit cleaner. Right now it looks a lot cleaner on the slides, but it's not really that clean. So that's definite, and we are working on it. That's one of the code cleanup things. So yeah.
I think the other one we've chose C89 to start with. The code, and then we realized that it does hurt our productivity quite a bit, and that has our code kind of mixed with C89 and C++11, and kind of probably should have looked forward.
What happens when the address of my target server changes? Is there any way to invalidate the connection because I have some kind of keep alive in the protocol?
You can cancel the calls. And were you saying something, Jayant? So you can cancel all the in-flight calls and destroy a channel to a server. So yeah.
But I have to do this on myself.
Yes. I mean, however, I mean, I must add that, I mean, if the URI completely changed, you have to do it yourself. But if the resolution, like, if now it's resolving to new backends, no, that's a different story. That depends on the LB policy and the resolver that you are using. Actually, Jan's talk from yesterday covers some of that.
So actually, if like let's say the DNS records change, and like one of the backend dies, that's gonna lead to re-resolve, and then new chat channels are going to be created to the new backends if the DNS re-resolve happens, and that happens when a disconnection happens.
There's one over there.
So as a follow-up to that, as far as the resolver is concerned, in cases of high availability, does it always essentially resolve to the current master? And then route calls, because the write completions and read completions are associated with the master at that point?
What do you mean by master?
So on the server side, the service itself can be HA'd.
Correct.
Right, and in that HA scenario, the reads and writes are essentially associated with a master.
The master, that's right.
So the resolution aspect of it is essentially always associated with the master. Is that something that GRPC handles, or is it the service side?
So it should be the. It has to be. If I understand your question correctly, so clearly the resolver cannot, like if you're doing a write, clearly the resolver has to resolve to the master, right? Not the. So that functionality cannot be at the GRPC level. Okay. That's something you have to handle. Probably have a different URI for the master, or like have your own custom resolver that can understand it.
Okay. Yeah. And a second question is the interop tests that you mentioned. Are they also open source somewhere to look at?
Yeah. All the interop tests are on GitHub repo, and you can look at them.
All interrupts are open source, and they're being used by lots of people. Like when Nginx launched, they started running those across Nginx, so they can use the proxy in between.
From your testing, did you just see any major performance difference between different OS or different threading models?
Oh yeah, and we experiment a lot with threading models, and it's still evolving. We keep experimenting with it. But one thing I can tell you is applications, like when you design your servers, when you arrange your servers in or clients in such a way that you're minimizing thread jumps, that yields the best performance. So when I say thread jump, and like GRPC makes it very easy for you to choose, like create your own completion queues. In the pictures I showed only one completion queue, but you can create as many as you want, right? Like you can create multiple completion queues, and you can associate a call with a particular completion queue. So as long as you minimize contention on the completion queues, and GRPC tries to like minimize thread jumps, and that usually yields the best performance. I mean, like Windows has a completely different model, and right now we've only been experimenting on the Unix platform, so I don't have much to comment on the Windows threading model. Yeah.
Me again. So just a question about the deployment of the backend. So would it make sense to have many endpoints for the different backends? Because like now everybody's talking about Istio and having like gRPC load balancing. So where we have apps from the outside coming in, will it be better to have like a single NLB and then going into Istio, and then Istio does the load balancing, or you have multiple NLBs and then public URIs and then do the client-side load balancing for the apps?
You want to take that, Jan?
I actually didn't catch the question fully, so I'm sorry.
So I think he covered load balancing yesterday, and there are multiple options, and it really makes sense in everybody's individual scenario, but yes, one of the models is either run a sidecar, Envoy or Istio type of this thing, and use that to do load balancing. And it's very convenient, so people do use it. So that's the benefit of it, and it can do fairly advanced load balancing. The cost is that you're going through a proxy. So if you're super latency or throughput sensitive, that may affect you, but other than that, it's a good option.
Yes, one over there. Are we okay on time, or I think?
Somebody will kick us out.
Actually, speaking of load balancing, is there any way to say like offload load balancing to the kernel and use IPVS or something? Have you guys experimented with that, and is it worth it?
Not that I'm aware of. Like, we haven't experimented with that.
Is there a reason you went for a multi-threaded approach instead of a single-threaded approach with an event loop?
That's a good question. So I'm not sure of the motivation behind the design choice.
I think that comes from our experience from previous generation study, where we learned that we could starve applications through single-threaded event loop. So we used a thread pool, and so that's why it's multi-threaded.
Okay.
Right.
Thank you.